Hey everyone, this is Brian. Welcome to week 4 of CSC 143. Hope you had a great weekend. We've reached a turning point in our class where we're going to navigate away from some of these object-oriented programming principles and turn towards data structures and how we can store and access data in performant ways. The first structure that we learned about already is the array list, and we've seen how the array list grows automatically to give the illusion of unlimited length. The next structure that we'll be learning this week is the linked list. And the linked list I think is pretty special because it's the first time we're going to really see how we can use references to support redirection of data and how we store data in different locations, such that inserting and removing data into our list is perhaps more efficient than what we do currently with the array list. We'll observe how the linked list behaves in contrast to the array list using these big O performance notation principles that we learned last week. Before we dive into that though, I want to talk about the third solid principles reading that I had to do last week, the L in solid, which stands for Liskov substitution principle. And it tells us that functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. Derived classes, of course, referring to child classes in a parent-child class hierarchy. And what the Liskov substitution principle really encourages us to do is to, once again, come up with some good foundational design for our base classes that have well-defined interfaces and specification for those interfaces, and then have these interfaces be fulfilled by child classes that offer more specific implementations. What it discourages us from doing is coming up with child classes as a convenience because we automatically inherit parent implementations, but those children classes aren't necessarily substitutable for parents. The example that they give in the reading, I think, is a pretty good example, and it's one to think about because it's so simple, but it's also so easy to kind of get wrong intuitively when we're writing classes on our own. The example they give is we have a high-level rectangle class, which stores a width and a height, and it also has these getWidth and getHeight and setHeight and setWidth methods. So getters and setters for these width and height dimensions. Then there's a child class of the rectangle called the square, where the square, all squares are rectangles, so it makes sense that squares should be squares should have rectangles as parents. Squares do the same thing, they have the same methods because they inherit from rectangle, but the square is going to enforce that the width and the height are always the same. Seems good, right? That's pretty intuitive. Squares are rectangles, so square should inherit from rectangle, and you can substitute square wherever rectangle is. But then we run into this weird problem that rectangles have variable width and height, and those two things may not necessarily be the same. But square says width and height have to be identical. And the consequence of that is if a function is observing a rectangle and chooses to set the width or set the height to specific values like 4 and 5 for width and height respectively, then we would expect to see that the rectangle has an area of 20, which is 5 by 4. But if we're actually using a square where that rectangle is being passed in, and the function is not aware that it's a square, and it tries to set a width of 4 and a height of 5, the actual output area is going to be something like 16 or 25, depending on whether or not the width or the height gets set to both the passed in 4 or 5 width and height gets set to the constant width and height that has to be equal to one another. So here we see a violation of this principle, where this function that takes rectangles has been given a square, which is a more specific kind of rectangle, and the square has behavior that the rectangle does not, which the function was not expecting. And as a result, the function is now behaving incorrectly because it had assumptions about the base class specification of the rectangle that the child class square was unable to fulfill, even though the function had no idea that there was a square here. Remember, the function, thanks to polymorphism, is just invoking methods on what appears to be a rectangle, but the methods that actually get invoked will be the methods defined on the square. So what the substitution principle encourages us to do instead is to separate these two things. Make rectangle one class, make square a different class. Don't have them commingle. And the reason it's kind of intuitive to us to make square be a child of rectangle is because we kind of learned in kindergarten that all squares are rectangles. So maybe it's sensible to say, okay, square should be able to substitute wherever rectangle is because, rectangle is like a superset of square. But I don't want you to think of inheritance in terms of superset and subset principles, because that's a very easy way for us to violate Liskov's substitution principle. Like, does it make sense that a queue, like a queue structure, is a subset of a list structure? Maybe. And in some circumstances, yeah, we could consider that. But also, a list has very different semantics sometimes than what a queue is. A queue is like a first in, first out structure, like standing in line at a movie theater. Whereas a list is a list. It's very flexible. We can append to either side, we can insert into the middle. Does it make sense to be able to cut into the middle of a queue? That's a question that, really depends on what kinds of interfaces you plan on exposing to your developer clients and how robust you want the contract of a queue or a list or whatever structure you have is going to be. On your next project after project 1, which is of course due very soon, and I want you to work on that first, so don't worry about this next project too much. On your next project though, when I ask you to implement the linked list, some of the bonus credits they'll offer you is this chance to implement a queue and a stack, some structures you'll learn about soon, as a child of a list versus as a container for a list. And you'll kind of see the implications of the differences between inheritance and containment. Inheritance, which we already know about, a child class inherits from a parent class and gets all its methods. Containment is where a class contains an underlying other class, an instance of another class, as a private variable, and then it's going to expose methods that allow clients to interact with this underlying class. And you'll get to observe the differences between these two different implementation strategies and kind of decide for yourself which one is better for these particular circumstances. Okay, that's a lot for the intro. Thanks for listening and enjoy the show. Hey everyone, this is Brian, recording another video lecture for CSC 143. In today's video, we're going to be covering linked lists, the first new data structure we're learning in this class. Before we dive into that, I want to do a quick recap of pointers and references again, because linked lists will involve a lot of reference manipulation. Recall that memory addresses are locations in memory, much like street addresses in real life. Every object in memory has a dedicated memory address that describes its physical location. Pointers are plain integers that store memory addresses. References, which we use in Java, are a special kind of pointer that have a strict type attached and don't actually expose the underlying memory address value, so we don't get to perform pointer arithmetic. In fact, in Java, every object variable declaration is actually a reference to the object. Java is a pass-by-value language, which means arguments and return types are copied. If objects are very large, and we copy by value, that's obviously very costly. But in Java, since everything is a reference, and references are really just pointers, that's actually not too difficult of a task for the computer to do, to copy the arguments and return values as references. Let's go take a look at reference test just to be clear on how the behavior works. I start out with the static class definition A. It simply is a container for an int I. Then I have this method called modify A, which accepts a single A inner argument and uses dot notation to retrieve the I field of the inner reference and set it to -1. In my first reference modify test, I declare a new A called outer with an I variable of 5, and then I call modify A, passing the outer reference to the function. Then what I discover is that the modify A method has adjusted the I value within the outer A instance such that it becomes -1. We can go ahead and run this test just to be sure. Great. Well, this happens because remember that in Java, every variable declaration is actually a reference, so outer is merely a memory address that locates this A instance. We copy that memory address into the argument inner, and the dot notation on line 17 is going to go look up the actual destination that the memory address points to and modify the I field within that physical location in memory. So assigning that I field to -1 updates the instance located at inner, which is in reality the same instance located by outer, which is why we get this -1 here when we look up outer's I field. Now let's check out this method called assign A on line 28. This time, I take a single inner argument, once again, but rather than modifying one of the fields, I'm going to go ahead and assign the argument to be a new instance. In my reference assign test, what I'll try to do is create an outer Then call assign a of outer with the I initially set to 5. We may be tempted to say, well, since we reassigned that argument to be a of -1, I should expect outer's I to also be -1. But this isn't the case. Remember that Java is passed by value, so arguments and return types are copied. But it also just so happens that in Java, everything is a reference. The reference outer, the memory address outer, gets copied to inner. But because inner is just a plain number, and the assignment operator merely replaces that number, assigning the argument, which is a copy of outer, doesn't actually have an effect on outer itself. This is different than the above example, because with modify a, we took that memory address that we received, and we looked up a field within that memory address, at that memory address, and modified it. Down here with assign a, I took a copy of a memory address, and then I replaced that copy with something else. Replacing that copy isn't going to modify the outer reference. Both memory addresses may be the same, but by the time line 29 completes, the inner reference here has been completely replaced, and the outer reference is no longer accessible. That's why down here, we still see that the outer reference is unchanged by the internal assignment. Okay, how about down here? Reference copy test. I make an a called foo of 5, and I make a bar that's assigned to foo. In Java, all variable declarations are actually references, so in this case, bar is a reference to the same underlying value that foo references. The double equals operator in Java performs reference equality. It checks if the underlying memory addresses are actually the same. Here, indeed, foo and bar are equal, because foo and bar are the same thing. They point to the same underlying instance. Then when I modify bar's I field to be -1, I also see that foo's I field gets updated, because bar and foo point to the same underlying instance, and this assignment on line 53 looks up the I field that bar points to and assigns it to -1, which of course is the same I field that foo would be pointing to. Then down here, I assign bar to be a new a of 9. Remember up here I said bar was foo, but here I'm replacing bar's reference with a brand new reference. The memory address stored inside foo has not changed. The memory address stored inside bar used to be foo, but now it's been replaced by whatever memory address is provided by this construction call. The outcome is that bar is now going to be its own instance, and foo is going to be its own instance. And this new a of 9 is not going to replace the existing new a of 5 that I initialized in the very beginning. Assigning bar changes what it references, but it's not going to change what foo references. So now we see foo is no longer equal to bar. Foo's I field remains to be -1, which I modified up here in line 53 and 54. And bar's I field is of course 9. Let's go ahead and run all these tests just to validate our hypotheses. Great. Having a firm understanding of how references work in Java is really going to benefit you when you start to work on these kinds of more complex data structures. We're going to see a lot of so-called indirection, where structures themselves will only have references to other structures or payload values like this integer I. And it's important that you recognize when a reference is being looked up versus when a reference is being replaced. Okay, now let's talk about linked lists. Array lists and the array are contiguous by definition. This gives us the benefit of fast indexing. I talked about last class how we can perform array indexing in constant time because all we have to do is multiply the array index by the width of the item inside the array and add that to the location of the array to get the actual offset. However, there are some other consequences to this contiguous requirement. First, we'll require that a contiguous region in memory has to exist in order to store that array. If we try to insert inside the middle, we're going to have to go copy all the elements that succeed that middle element forward by one index. Same thing happens when we try to insert at the front. If we try to insert at index 0 and shift all the elements over, we have to go walk the entire list and shift all the elements over by one index. Deletion is just as bad. If we remove a node, we have to shift all the successive elements over by one index to fill that gap. Let's take a look at LinkedListTest just so we can familiarize ourselves with the interface. Here we've got a function called populate. It takes an array list as an argument of strings, and it adds John, Paul, George, and Ringo, which of course is the 4 Beatles, into the array. Let's run all the tests so we can move on. In our first test, array list insert test, I build the array, I pass it to populate so it fills up, and then I use the get method to retrieve the indices. Pretty simple. Then when I try to call this add method at index 0, what it's going to do is it's going to insert the value at the index and then shift all the successive elements to the right, which of course is going to be O of n, because I have to go walk the entire array list and move all the elements over. Amy, who is inserted at index 0, becomes the element at index 0, and then John, who was previously at index 0, got shifted to index 1. Similarly, the add method works in the middle. If I specify an index that's in the middle of the array list, like index 2, for Barry, Amy and John remain at indexes 0 and 1, whereas Barry now takes up index 2, forcing Paul over one index to index 3. This, of course, is also going to be linear time, big O of n, because we're going to have to move up to n elements forward by one index, and requiring us to traverse pretty much the entire array to do so. Deletion is very much a similar story. If I call remove on an index, the array list is actually going to shift all those successive elements forward to fill that gap. So if John used to be at index 0, then Paul gets shifted into John's spot. We can do the same thing by trying to remove in the middle. Paul will remain at index 0 because Paul was always at index 0, but then Ringo shifts forward and takes what used to be whoever was in index 1 here. I think that's George, yes. There's one silver lining to this story, which is removing from the end. Just like how appending to the end is mostly efficient, removing from the end is always efficient. If we remove the index at length -1, remember, indices are 0 indexed, or arrays are 0 indexed, so indices start at 0, but counting is always starting at 1. So the length of the array -1 gets us the last element, and removal doesn't require us to shift any other elements around, because there's no more successor elements to the last element. So that one's always going to be O of 1. Okay, so that's how the array list methods are going to behave for us. And what that's going to do is it's going to motivate us to think about this contiguous requirement and the certain limitations that it has and its inflexibility, so to speak, when it comes to mutation and insertions and removals that involve shifting elements around and their respective indices. The linked list is a data structure where each element stores a value, sometimes called a payload, and a reference to the next value. Rather than store the data contiguously, like with an array, elements are going to be stored separately. Then those elements are linked together with pointers or references in a chain. By chaining several values together using references, a linked list is formed. Let's take a look at the whiteboard to see how that looks. Let's start out with a description of the array list. Suppose for a moment that I had this class A, which was simply a container for an integer I, and I declared an array list of type A, and then I added two elements, new A of 0 and new A of 2. These construction calls, of course, are going to generate their own memory locations and instances. So we have an A of 0 here and an A of 1. And then the array list, by nature of it being contiguous, will start out by allocating a space to store all of its references, and then the indices are going to go refer to the A instances underneath when I use that get method to retrieve an index. Let's see now how the linked list does it differently. Let's start out with this class node. This class node is a container for a payload, kind of like an individual index inside the array list, but this class stands alone. It's going to contain a value as well as a reference to the next value. Now, how are we actually going to build this list? Let's declare a head, assign its payload to have an a of 0, then have its successor, the next field, be a new node, so it can be another container for a new a, and then set that payload value of the successor node to be 2. So here we have our head node. It's got a reference to an a instance. It's got a pointer to another head node. And then that node itself points to another reference, to an a. So the clever thing about this chaining operation is that it lets us essentially split up this array list structure and break out these individual indices such that those indices are represented by these individual standalone buckets. One interesting observation here is that this is the head node, the left node of the entire list, but you can also see how this second node is the head node of its own sublist, and so forth. This node stands alone. It could be the second element in a list. It could also be the first element within its own list. Traditionally, we're going to keep track of the head reference and possibly the tail reference for a linked list, so we can always know which element comes first. Suppose for a moment now that we wanted to remove an element from the head side of the list. With the array list, I had to go shift all those elements forward by 1, which is an O(n) operation. But just as I just described how the second node in my list could theoretically be a head for its own list, removing a node from a linked list is just a matter of reassigning the head, the reference to the head node, to point to the second node within the list. The clever thing about this strategy is that the Java garbage collector, which is going to realize that the head node, the original head node, is no longer being referenced, is essentially going to take it away. And then, as we observe this list, the head now points to the second node, and the tail stays at the same location. Let me rephrase that. When we're using this list, we're going to treat it as if it has a head and a tail, and a series of elements in between. By nature of moving the head forward by 1 element, I lose access to the original head. And we can now think of the list as being composed of the new head, chaining elements all the way to the original tail. The outcome of that is that it's as if the list itself dropped the head element and now is only composed of all the elements between the head and the tail. So to summarize, the linked list has 1 element and 1 node each associating with each element. The nodes are going to be stored separately, unlike the array list, which requires all the elements be stored contiguously. A consequence of storing elements separately is that we lose access to fast indexing. Remember how indexing in the array list was always O of 1, because all we had to do was compute the offset from the list? Well, here, we don't get that luxury. With the linked list, just because we have the head, we don't know anything about the location of successor elements. If I'm trying to reach node 4, and I start at the head, I can't do something like take the number 4 and multiply it by the size of the elements, because no longer am I guaranteed that the 4th node in the list is going to be positioned exactly 4 times the width of the item beyond the head node. Instead, what we're going to discover is that indexing in linked lists is going to require us to iterate over the list until we reach the index we're looking for. This is very much foreshadowing for how the linked list is going to behave. What we're going to find is a certain degree of flexibility that the array never had, because we can move stuff around, we can manipulate references to change up the order of the list very quickly. However, by nature of the list no longer being totally contiguous, we no longer get this really nice benefit of being able to jump from the head to any location at will. The linked list itself is still iterable. Walking the list is just a matter of referring to the next fields of each successive element. And we'll find that it's going to be easy to append to either end. If I want to append an element to the head, I just create a new node that becomes the new head and have that new node point to the old head as its successor. If I want to append an element to the tail, then I just set the tail successor to be that new element and then shift the tail reference to point to that new element. Okay, let's turn back to the README and see how we can do this in code. We'll start out with node.java, which is of course going to be this container for an element. Node is a generic type and has a T payload and a reference to the next field. I've also gone ahead and defined a constructor that simply takes a payload, and the next field is going to default to null here. The second constructor takes a payload and a next argument. So this node can effectively have a value as well as a successor right away. Now let's take a look at node test. I'll go ahead and run all the tests in here just in case. Great. Let's build our very first linked list. Node of type string is going to have John inside. And I assert that John is indeed stored inside the payload there. Next up, I create a head node and I chain together John, Paul, and George. This is essentially constructor chaining going on. Let me go ahead and adjust the indentation so it's a bit easier to see. Or harder to see, depending on your preferences. So what's happening is I declare this new node that has John inside, and as John's successor argument, I have these nested nodes here. The nested nodes include Paul, who himself has a nested node successor of George. The outcome is John is succeeded by Paul, who is succeeded by George. We can visualize this with this comment here. We've got our head reference, which points to John. John has a next field who points to Paul, and Paul has a next field that points to George. So when I take a look at head's payload value, that's of course going to be John, the first node in our list. Let's make a new reference called tail. This time we'll make it point to head.next. Head's next field is going to be Paul. So then I can see that Paul is indeed inside tail's payload. An interesting thing to observe here is that tail no longer points back to head. The tail points to this Paul node, but inside the node container, I did not have a previous reference. This is what a singly linked list is going to look like. In this kind of list, each node simply points to a successor. So in this case, tail is pointing to a sublist of the original list, and tail itself is actually the head of a list. Now let's move the tail pointer forward by 1. I'm going to assign tail to be tail.next. Tail currently points to Paul. Paul's next field points to George, and I discover that tail's payload is indeed George. Then I move tail forward one more time. George's next field is going to be null, and that's what I get at the bottom here. If I try to look up the payload field of this null pointer, I get a null pointer exception. This is something that students are going to run into a lot when you work on the first project. Or, sorry, not the first project, but the next project, which is going to involve writing a linked list. Whenever you hit this null pointer exception, I would really recommend using step-by-step debugging. Remember to click on the gutter area here to pause the code, and inspect the underlying values of these node references. The moment one of them becomes null is when you know that that is likely the cause of a null pointer exception. When you try to do a lookup of a field on a reference that's actually null. After all that manipulation of the tail, the head reference still exists at the top of this code, and that's still going to point to John. So we could start from head again and walk the list once more. All the elements still remain referenced from the head, so none of them are going to get garbage collected. Suppose for a moment that we wanted to go deep into the list and assign a field. Head currently points to John, the next field points to Paul, the next field after that points to George, and we want to assign that George to be Jacob instead. We could do this sort of reference chaining here by looking up the field of the field of the field, but that obviously doesn't scale up. If we have a list any larger than this one, you're going to be typing next a whole bunch of times. Fortunately, we are programmers. We have structures like loops to handle that kind of reference lookup for us. Here is a very basic loop that walks all the references inside the list. I create a front reference that's a copy of head. I ask, is the next value null? If not, then I can walk one step forward and move that front pointer to the next node inside the list until the front pointer reaches the last element inside the list. Once this loop exits, I would expect that front points to whatever field is at the very end of this list. I believe that would be this node here, George, which we can also get to from head.next.next. I really do encourage you to understand this looping structure here. It's a little strange at first to see how the pointer gets moved forwards and how front is actually shifting down each element inside the list. But I assure you it's not super complicated, and what we learned about how references work in Java and how they're really just pointing to other underlying locations, we're going to find that this looping structure is actually very natural to us, because it's just a matter of examining the successive fields and then bailing out when the front pointer's successor itself becomes null. What I discourage you to do is something that looks like this. Head.next.next.next, which is going to be a null pointer, and then trying to assign that null pointer field to something, which of course is not going to work. Okay, now let's look at this from a different perspective. Suppose for a moment that I made a head node with John that didn't have an immediate successor. Then I created a new node with Paul that pointed to the head node, and I assigned that new reference returned by the construction to be the new head. The outcome is that Paul is going to have a successor that is John, and head now points to Paul. Same thing down here. If I try to do a new node of George that points to head, and assign the outcome of this construction to be head, then the head is going to point to George, George points to Paul, and Paul points to John. Looks like IntelliJ is complaining that I haven't put these angle brackets in. Let's go ahead and do that and fix it. The interesting observation I want to make here is that this example builds the list in the opposite direction. If we push to the front, this causes the names to be reversed. Remember at the very top of this 3-node chain test, I nested the construction calls of John, Paul, and George, such that John's successor would immediately be Paul, and Paul's successor would immediately be George. Down here, instead, I start out with the head as John, then Paul becomes the new head, pointing to John, and then George becomes the new head, pointing to Paul. I see that George is our first payload. I move my head forward by one node such that head is going to point to Paul. Paul becomes the next payload. I move the head forward one node to point to John. John becomes the next payload. I move the head forward one last time, and I see that head now becomes null because John has no successor. Now that we've moved the head all the way to the very end of the list, there's actually no way to go back to the predecessor elements. Remember that this is the head that we used from the very beginning. We set head to point to George, then through all these lines of code, we moved the head reference to point beyond John, such that it pointed to nothing. Because we did not save references to these nodes anywhere, we didn't make copies of these references, Java's going to realize that all of those nodes are no longer being used, and in effect, they're all going to be garbage collected. This is one way of deleting elements of a linked list is just to stop referencing those elements. In some other languages, like C, where you're going to have to manually manage your memory, you don't necessarily get this luxury of being able to just avoid referencing something you no longer care about, because that object will still be live in memory. In Java, however, Java is a garbage collected language, which means that it's going to be smart about what elements are referenced and what elements are not referenced, and it's going to go take care of the garbage when we have elements that are no longer referenced from any location. Now that we know how to build a linked list, let's analyze the runtime cost of linked list operations. Indexing, to reach the ith element, is actually going to be a linear time process. This is because we only have immediate access to the head and the tail nodes. To get to the ith element within the list, we have to start from the head and then walk up to n elements to reach the ith element. This is in contrast to the constant time performance of the array list. With the array list, all we had to do was compute a simple memory offset from the very beginning of the array to get to the ith index location. Iteration is always going to be O of n. We can't avoid having to look at n elements if we want to walk the entire list, so that's unchanged. Inserting to the front is perhaps where the linked list sees its first advantage over the array list. In order to insert to the front of a linked list, all we have to do is update the head node such that it becomes a new node, and this new node points to the previous head node. The outcome is that from an external observer's perspective, the linked list now has a new front node, and then the rest of the list just happens to be chained onto that new front node. This is very much in contrast to the linear time performance of the array list, where in order to insert into the 0th index, we had to shift all the existing elements over by one index, which is a linear time operation, O of n, and then insert that new element inside index 0. We have a similar story for inserting into the back. If we have a tail pointer, a reference to the very last node of the linked list, we can quickly add elements onto the linked list by creating a new node, having the existing tail point to that new node as its successor, and then updating the tail reference to point to that new node. If we didn't have that tail reference, we would of course have to walk the entire list to reach the last node, but in most circumstances, when managing a linked list, we will have that last node reference, in order to have this fast insert back behavior. Array list performs kind of similarly. Remember, with the array list, we get on average O of 1 insertion performance because the expansion process doesn't have to happen that often. However, every now and then, the array list does need to expand, and we have to use a linear time operation to copy all the existing elements into a new array that has twice as much space. Inserting in the middle is kind of an interesting story. To reach a middle node with the linked list, we still have to use iteration to reach the ith node that we're trying to insert at. And the same goes in a way for the array list, because we once again, just like inserting the front, we have to make a gap be available at the ith index and shift all the elements over. However, let's say for a moment that we're already iterating through that list. If we were already iterating through the array list, then we don't actually get an advantage of being at the exact index that we're trying to insert into. We still have to shift all the successive elements over. However, for the linked list, if we already happen to be at the location of the node we're trying to insert into, then we just have to wire up the pointers such that the new node we're trying to insert becomes the replacement node for the ith node we're trying to replace. What do I mean by that? Let's suppose for a moment we're trying to insert a node at index I. We can walk the list up to index I minus 1 and set its next reference to point to this new node that we're inserting. And then we'll have the new node that we're inserting have its next reference point to the previous ith location. This is a great luxury to have because in a lot of operations, we are walking the entire list. Iteration is a very common process. So we could argue that this O of n iteration is inevitable, and if we happen to be at the location in which we need to insert, then that's just a very convenient couple of steps to do. Array list, again, doesn't give us that convenience. Iterating or not, in order to insert inside an array list, we have to make a gap, by shifting all the elements over and then insert that node into the respective index. Removing nodes in the linked list is very much a symmetric story. If we try to remove from the front, all we have to do is move the head node up one node to be the node that the head node currently points to. To remove from the back, if we have access to that tail pointer, we could move that tail pointer back one node to point to its previous node. Now, if we have a singly linked list, this is actually technically not possible, because we don't have a way to get from the last node to the node behind it. However, what we're going to learn about pretty soon, and it's what's going to be your next project, is this doubly linked list. That's going to not only include references to successive elements, but also references to predecessor elements. With that in mind, if we had a doubly linked list, we could very easily take a tail node, shift the reference to the previous element of that tail node, and make that the new tail. With a singly linked list, we'll have to do it by hand, by walking the entire list until we reach the node right before the last node, and then making that node right before the last node be the new last node. Removing from the middle is very much the same story as we saw from inserting into the middle. It's going to be O of n to reach the middle node, and O of n always for the array list because we have to go shift a bunch of elements around. But if we happen to already be iterating during this operation, then removing a node is just a matter of wiring up this node's predecessor to point to this node's successor, such that this node that we're removing is skipped during the process. So overall, what we see is that the linked list is a bit more flexible than the array list. By nature of it not being contiguous, we're allowed to add elements onto either end, remove elements from either end, and insert elements into the middle of the list with not too much complexity. In contrast, the array list requires a lot of shifting of elements around. If we ever try to insert at the front of the array list, we have to shift all the elements over by one index. We get the advantage of generally fast appending to the back, but we still have the occasional pitfall of a linear time operation to copy all the elements into a new space. Deciding whether or not you want to use a linked list or an array list in your program very much depends on the circumstances. If you think you're going to be doing a lot of inserting to the front and removing from the back, for example, maybe you're building a queue-like structure like a line of people in real life, then perhaps the linked list is for you. If you're going to be doing a lot of indexing, that is looking back on existing references, then maybe the array list is better because you get that much faster indexing performance. We've talked about how interfaces can abstract away runtime cost. Java interfaces like collection and the classes that implement them abstract away the complexities of the underlying implementation. This simple node structure that we built to build up these linked lists act as an internal container that manages the value being carried and the next item in the list. However, as you've likely seen, managing these nodes is pretty inconvenient and complicated. If we want to index over a linked list using just node references, we have to write our own loop. If we fail to preserve the head node, we can accidentally lose access to the entire list. If we want to keep track of the length of the list, we have to count every node that's being inserted or removed. And the act of inserting into the middle or removing from the middle can be hard to get right, because we have to make sure to wire up the neighboring pointers to point to the right locations. Thankfully, we are programmers, we've learned about abstraction in this class, and we've learned how methods exposed by a class can be a layer of abstraction against the underlying complexities, such as the management of these node classes. Let's write a wrapper class that manages this node object for us and reveals a simple interface for a linked list. Let's go look at LinkedList.java. Here I've got my public class LinkedList, and I'll go ahead and say it implements iterable. Remember, the iterable interface is a library interface in Java that just says, hey, my class is iterable. You can walk this type and iterate over all the elements, and I'm going to do that by offering an iterator, which we'll see very soon. For my linked list, I'm going to make it manage a head and a tail node, as well as a size, so I can get that size value without having to walk the entire list. I start out with the default constructor that does nothing. The list is empty, head and tail are going to be null, and size is going to default to 0. Then I'm going to have a linked list constructor that takes an iterable. What this is going to do is it's going to effectively convert whatever argument that you passed in that is an iterable type and turn it into a linked list. This constructor is going to enable me to pass any iterable type, which is going to be any kind of collection, including an array list, and get a linked list on the way out. To walk an iterable type, I can use this for each loop construct, which of course is going to do the same thing as invoking the iterator method on the iterable and pulling out an iterator and then calling the next method a whole bunch of times. I'll start out with an empty list where the head is going to be null and the tail is null. For the very first element in my list, I'll set it up so that head points to this new node and tail points to the existing head, because head and tail become the same node if it's a one node list. In this else case, I know I already have an element inside my list, so let's append an element to the back by saying tail's next is going to be a new node that contains the value, and then updating the tail reference to point to this new tail that we've just created. Finally, now that we're done processing a value inside the iterable, let's increment the size. The outcome of this constructor is that now we're going to have a series of nodes all chained together in a linked list form that essentially copies whatever values were inside the iterable that we passed in here, whether it be an array list, a set, or some other iterable structure, like that range that you built for Project Zero. Now let's check out this push front method. The push front method is going to append a value to the front of the list, and we're going to build this out very similarly to how we built the constructor. We only have two cases to consider. Either the list is empty, or it's not. If the list is empty, then our head and tail nodes become the same thing. They become the single node that we inserted. Otherwise, we'll make a new front node. This front node is going to be the new head, so it needs to point the existing head to preserve all those elements, and then we'll replace the head reference with the current front. Finally, we'll increment the size. Pushback looks very similar. Pushback is going to append a value to the very tail of this list. I have two cases. Either the list is empty or the list is not. If the list is empty, we'll make a new node, have that be the head and the tail node. Otherwise, we're going to build a new back node because this pushback is going to add a new tail to the end of the list. Then we'll set up the existing tail such that it points to this newly inserted back node. And then we'll set up our tail such that it becomes this newly inserted back node. And of course, we increment the size of the list. The size method is going to return size. Makes sense. Now check out this class definition inside the linked list class. This is an example of a nested class definition. We're not going to use this too much, and I'm not going to press you too hard about it. I'm not going to press you at all about it in terms of syntax, because it's more of a language-specific feature, but it is a convenient way for you to define helper classes within a class that can be reused. In this case, I have this LinkedListIterator defined, which implements the iterator interface. You can kind of see where this is going. Remember that, by nature of linked list being an iterable type, it must have an iterator method that returns an iterator. That iterator type is going to be this linked list iterator that I'm building out here. The iterator is essentially a reference to a particular node inside the list that is going to keep track of the current phase of the iteration. As I walk the list using the linked list iterator, I'm going to be invoking the next method on the iterator to push the reference forward until I finally reach the last node inside the list. I'm going to do this by keeping track of the head node of the current list and have that be the current node that I'm examining during iteration. To get the next value, I'll just retrieve whatever payload this reference is being pointed to, and then shift up this head reference that I'm keeping track of inside this iterator up to the next node. And then I'll return the original value that I just received. I know my iteration has stopped when I've run out of next values, and that my head reference has become null, because eventually my head is going to reach the tail, and the tail has no next element, the tail's next field is going to be null, and then this is going to return true. Now down here, because my linked list class is an iterable type, I'm obligated to have a method called iterator that returns an iterator. And I'm going to build a new linked list iterator, which of course fulfills the iterator interface, and pass it along the head reference, the current head reference inside the linked list, such that the linked list iterator can now keep track of the head and then walk the remainder of the list via references to head next field. Okay, so hope all that makes sense to you. If it doesn't, I actually recommend you rewind this video until you reach the very start of this class explanation and think about this through your head in terms of how these individual nodes are being managed. Remember that this linked list class is very much an abstraction around these nodes. These nodes are responsible for making up the actual linked list. Rather than us manually messing around with head's next pointer and dealing with node references ourselves, we have built ourselves a class that does some of the methods that we would expect on list structures, like pushing nodes onto the front. The great thing about this interface that's being exposed by this linked list is that the client actually never has to know what a node is. In the array list, for example, we never access the underlying raw array. That's not necessary to us. Instead, we get access to methods like add, which pushes elements to the back, and get, which retrieves indices, values at indices inside the underlying array. The similar story with this linked list class that we've built is that we've built a list abstraction that takes away the need to think about these individual nodes underneath and just treats it as if it is a list structure that lets me push values to the front, push values to the back, and then lets me walk elements inside that list using the linked list iterator provided. Even the return type of this next method call returns the underlying values inside the list and not the nodes themselves. Now let's take a look at how this is all used inside the linked list test. We'll go ahead and run it just to be sure. Great. I start out by building a new linked list. And then I push back the values foo, bar, and baz, which gives me a size of 3. Then I invoke the iterator method on the list, which I know is possible because the list itself is an iterable type, which gives me an iterator of type string on the way out. I can manually walk the elements inside the list by invoking the next method on the iterator. The first call returns foo and shifts up the reference inside the iterator up by 1 node. The next call to next returns bar and again shifts up the internal reference of the iterator to the next node inside the list. And the third call to next returns baz, shifting the internal reference one more time beyond the tail of the list, such that it becomes null. Then I can assert that has next becomes false. Now let's see what happens if I push to the front. I build a new linked list, which starts as empty. I push to the front, baz, bar, and foo, which of course gives me foo, bar, baz in list order. My size is indeed updated to 3. I pull out an iterator and I get foo, bar, baz because the frontmost element was foo, the next was bar, and the third would be baz, ending with an iterator that is completely exhausted and has no more elements to point to because the final call to next updates the reference inside the iterator to point to the tail node's next field, which is of course null. Now let's see what happens when we try to use the for each loop construct on our linked list structure. We build a new linked list, we push back the values foo, bar, and baz. And I'll go ahead and build out this raw array list here with the values foo, bar, and baz. The reason I'm doing this is so that we can have an expected list to compare our linked list against for the sake of testing. Here's another usage of the Java library linked list called names. Inside names, what I'm going to do is I'm going to first walk the outer linked list that I just built using this for each loop, which is possible because this outer linked list that we built is an iterable type and supports the iterator method. I'm going to then invoke the add method on the names linked list. The names array list. such that it contains the same values that the linked list produces when iterated over. And what I should expect to see is that the names array list built from the linked list becomes the same thing as this array list here, composed of foo, bar, and baz. And I see that indeed it does work out. The equals method on the array list is going to do a value-wise equality of all the internal values between the two lists and expect them to be the same. So what I hope to do is demonstrated by these tests for this linked list is how easily, well maybe not so easily, but how effectively we can build out something that looks a lot like an array list, but is composed of a very different infrastructure underneath. The linked list stores elements very differently than the array list does. However, the exposed interface, whether it be pushback or add or iterator, looks very much the same. This is very much how those Java library classes like the array list are built. We have this complex behavior underneath, such as the automatic array expansion of the array list, that is abstracted away via these relatively simple to understand methods like add. We will do the same thing with our data structures by building out classes that have complicated behavior underneath, but abstract away these complications via these simple method calls that manipulate the list. Okay, seems like that's all I've got for today's linked list lecture. Again, if this is a lot to digest, I really recommend you rewind this video, start from a spot that you're comfortable with, and try watching it again to recognize the updating process of the linked list. Make sure you also have a firm understanding of pointers and references. Linked list manipulation involves a lot of reference updating because each node has to point to its neighboring nodes. Your future project is going to be a AA linked list, and building out the methods for a linked list such that each individual node not only points to its successor, but also points to its predecessor node. You're going to find a lot of things are quite complicated, such as inserting into the middle, where you have to update both neighbors surrounding this new inserted node in order to update the entire list. This is very much where you're going to run into a lot of null pointer exceptions, and that is when I also encourage you to, of course, use the included IntelliJ debugger and walk step by step through how the list is being managed. And now that I bring it up, I actually think it's worthwhile for us to do a quick exercise in debugging to see how the linked list behaves. Let's drop back into the linked list test and put a breakpoint on one of these tests. Let's go ahead and put it on pushback because I think that's one of the simpler ones. Now I'll go ahead and start debugging, so it'll stop execution when it reaches this line. If we look at the list field, we can pop it open by opening the variables in this tree here, and we see that the internal properties of list are currently size of 0, head and tail are currently set to null. Then let's go ahead and step into this pushback function. Now that we've dived into pushback, we can walk through the process of how this list gets updated. The value I'm trying to insert is foo, the head node is indeed null, and the tail node is also null because the list is empty. That makes this if condition true. I walk into the condition and execute the values. I build out this new node. I make the head and tail be this new node that I just built, and I increment the size. Now when I leave this function, and I take a look at my list field again, I see that the list now has a single node. This node at 1164, which is the same for head and tail. My size is also 1. You can continue to pop out these individual fields inside these variables to see what the underlying fields are underneath. List contains nodes head and tail. A node is just a container for a payload value and a next field. So I can take a look at the underlying values within each of these classes contained within the list, which I think is pretty cool. You can keep on going into even the string inside the payload, but then it gets less and less useful. Let's keep going. I step back, step forward. And now that I've reached this third line, I see that the size is updated to 3. My head points to foo. its next points to bar, and bar's next points to Baz, which of course is also the same as the tail node here. Then I step forward, I pull out the iterator I. Iterator I, let's go take a look at what that is. Iterator I has a single head field that points to the foo node, which of course is the same thing as the head of the foo, which is the same thing of the head inside this list. We can verify by those numbers on the right here, which I think are actually memory addresses, or they might actually be the hash values, which I think is more true. Node at 1164 is the same thing up here as node at 1164, so I know that my iterator currently points to the same head field as my list head. Now when I walk over my iterator, I see how my head node inside the iterator is being updated. My list node head still remains foo, because that shouldn't be changed, but the head node of the iterator is now bar, because that's the second value inside my list. I walk over one more time, and I see that the iterator once again becomes updated with the head node being Baz. And if I call next one more time, what I should expect to see is that this head field is going to be updated to tails next, which is going to be null. We can go ahead and dive in, step into to see what next is doing. I'll click on next. I see what it's going to do is it's going to return the value Baz. It's going to update the head field within the iterator to point to head.next. We can even look at what head.next is, which is null. We step out by returning the value. We step over one more time, and I see that the internal reference pointed to by the iterator is now null, so that the iterator itself is exhausted. Remember that iteration shouldn't have an effect on the list being iterated over. The iteration step is just a matter of observing the values that are being iterated over. We can think of this iterator very much like the range iterator from your first project, and the list being like the range, which is just a defined sequence of values. I step over one more time, and I should be at the end of my test. Okay, I hope that little exercise gave you some more insight on the debugging process and how the list is behaving underneath. I encourage you to pull out these class notes, download them on your own machine, and run this list, LinkedListTest, and walk through the behavior on your own. As an additional exercise, if you want some extra preparation for the AA linked list project, which you're going to dive into in a couple of days, I suppose, consider trying to add some methods onto the linked list, such as remove or insert, or even something as simple as get for a particular index, and create that layer of abstraction between the client of the linked list and the underlying behavior of the linked list to make those operations happen. Okay, I think that's enough content for today. Thank you for listening, and I'll talk to you next time.